got compound interest. We've done some compound interest using the simple interest formula. We had to do multiple calculations to get to our balance. Well, we have a formula, the compound interest formula, that does all that for us. And what we do is we take the principal, the rate, the number of times it's compounded, and the number of years, plug them into this formula, and you get the ending balance. So it actually counts for the interest for you. We have what's called an annual percentage rate. Oh wait, hold on, let me put this. This is only one deposit though. So this formula is if I deposit $100 in the bank and then I don't touch it, I don't put money in, I don't take money out for 5 years. Okay, so this formula doesn't account for if you put in deposits in like every month or something. There's a different formula for that, which we'll go over in another section. You have your annual percentage rate. This is the rate that is used to compute the interest. And then you have an annual percentage yield. This is the amount of interest you've actually earned. Because when we talked about the difference between simple interest and compound interest, you know there's like a little, 50 cents more or whatever per year that you earn. That changes the percentage. So if you actually calculate, if you go backwards and you have your interest and you know how much interest you got, and you calculate that based off of the money that you put in, you get a different percentage. That's the yield. This is what the banks advertise. Because it's higher. So if you're earning 5% interest, the yield might be 5.2%. So they'll advertise the 5.2 because that's higher, and so it sounds better. That's when you're earning interest. Now when you're paying interest, you still have the same two things, and they'll advertise the percentage rate because it's lower, even though you're actually paying a little higher because of the compounding. Okay, so on the compound interest formula, B is your balance. Okay, so that's the money that you put in the account and all the interest. It's like the actual balance in the bank that day when you calculated this. P is the principal. Okay. R is the rate. What color do you think? This one? That one. N you have in two places, but it's the same number in both places. This is the number of times compounded per year. Okay, so if you're compounding annually, N is going to be 1. If you're compounding quarterly, N will be 4. If you're compounding daily, N will be 365. Okay. And then T is time, and that's in years. So if you're given months, you have to convert it to years. And so what this formula does, do you see how there's this 1 plus, and then it has the rate divided by n? That 1 plus is what brings your interest in. So when it's doing the calculations, this 1 plus is what adds the interest in and is calculating new interest on top of interest on top of interest. $1,650 for 3 years at 3% interest compounded daily. Okay, so this is going to be N equal to 365 because there's 365 days in a year. Okay, there's our formula. T is 3. R is 0.0. 0.03, I don't know what I did. And P is 1650. Alright, so I'm going to plug these in. Okay, the first things you're going to want to do is this division here and this multiplication here. I usually do this first and this second, because this is going to give me this ugly string of decimals and I don't want to write them all down. So what I'll do is I'll go ahead and get that multiplication in there. So I have 365 times 3. And here's what I usually do. I go, okay, that is 1095. And I just go ahead and cross it out, put the right number up there. And then I go, okay, 0.03 divided by 365. I'm going to write it off to the side over here. Because it doesn't divide evenly. Yeah. Here, yeah, I'm saying do this first and then do this second. Maybe I should circle this so you know I'm not saying divide by 2. How's that better? So I get a long string of decimals. That's not the whole number. It doesn't divide evenly. Sometimes it will, and you'll get like a nice 0.05 or something, but most of the time you get this long string of decimals. So the next thing I do is I go ahead and add 1 to that. I just leave it in the calculator and I do plus 1. And then I get 1.0082 whatever. Okay? I haven't cleared anything out. I just pressed enter on that. I did the division, then I did plus 1. The next thing I have to do is take this answer here to the exponent. That's the 4th step. Okay, so I hit my exponent button and I plug in 1095. And now I have 1650 times 1.0941702336 whatever. Okay. But I don't clear that out. I just go ahead and hit times 1650. That's the most accurate way to do it because you haven't lost any data. I didn't round at all during the process. So once I've done that multiplication, now I'm going to round to the nearest penny. And her balance will be 1805.38. Sharon's going to deposit $8,000 in a 1-year CD at 3.2% interest compounded daily, and we want to figure out her percentage yield. Okay, so to figure out percentage yield, our first step is to find the balance, and then from there we find the interest, and then we divide by the principal, and that equals the yield. So step 1, we're going to use the same formula. So our balance is going to be our principal times 1 plus our rate divided by n. We're compounding daily, so it's 365. And it's 365, it's 1 year, so times 1. Well, I don't actually have to do that multiplication because I know that anything times 1 is itself. So that's just going to be 365. So I'm going to do 0.032 divided by 365 plus 1 raise it to the power of 365, and then multiply it by 8,000. She's going to have 8,260.13. Okay, now I need to find out how much of that, like what's the interest. Well, to find the interest, I take her new balance and I subtract how much money she actually deposited. So she earned $260.13. And then to divide, I take that and I divide it by the principal, and that will give me my yield. Okay, so 260.13 divided by 8,000 is 0.032516 and other stuff. It said to the nearest hundred, so that's going to be 3.25%. So she was being paid a rate of 3.2%, but because it's being compounded, she actually earned 3.25%. So you can see the yield is a little higher than the rate. Does that make sense? And this extra 0.05 right here is because of earning interest on top of interest. Here? Here? Yeah. I divided that, and then I added 1. Hold on, let me pause it. Where's my button? I need you to take it off too. Do you know what an asymptote is? Okay. I'll come back to this screen. Hold on one second. Okay, so if we have a function, let's say we have an exponential function. And an exponential function is a function that grows exponentially because it's some number to the exponent of x. And every exponential function looks pretty much like that. Okay?
Oh, I've got something similar, but I did that like Algebra 3.
And this will never touch the x-axis. Because no matter what number I put in for x, negative, if I keep going negative, I just keep getting a fraction with a smaller, or like a bigger and bigger and bigger denominator. But it never actually will ever hit 0. It can be like 1/5 gazillion. That's not a real number. But it will never hit 0. And what happens is, in math, especially calculus engineering, there are functions that won't ever hit a number, ever, but we need a number to put in to continue calculating. And that's what a limit is. So the limit here, as x went to negative infinity, as it kept going towards negative infinity, we would say it was 0. It never actually touches 0, ever, but it gets so close to 0, it might as well be 0. And so then we say it's 0, and then we can do more math. And there's other things, other functions that'll have asymptotes, like maybe here and the function will bounce up and down between them, and just weird things that'll happen. And we'll say that if x is here, the limit is this value, and if x is here, the limit, it never actually touches it, but it gets so close, it might as well be that number. Does that make sense? So basically it's kind of like estimating. And so we assign a value to an unreachable thing. Like you can never get there, but we just, okay, it's getting close to this, so we just say it might as well be that and be done with it. Okay. We have finite is represented by a real number. And is reachable. Okay. And then you have, oh, and it ends.
Comes up with what value?
Assigning values. Yeah, so we assign values to unreachable values. So you have finite, which is represented by a real number. It's reachable. It has an end. Sort of like our bank accounts. Right? They have an end. And then you have infinite, which is unreachable. And it doesn't end. And it's a concept, not a number. Okay. So when you talk about infinity, and people say, oh, it's infinity. Infinity is not a number. It's an idea. Because you can't, as long as you can think of a number, you can always add one to it. You think of the biggest number you can think of, add one to that. Then add one to that, and add one, and add one, and add one, and add one. And if you started it with one, and you kept adding one until you died, and then your children took over, and they kept adding one until they died, and their children's 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 children, the whole line of your ancestor, your whole descendant line, could continue adding one forever. Yeah, it would never end. So when we talk about infinity, and even though there's a symbol for it, it's not an actual number. It's just an idea. And it's the idea that numbers go on forever. But infinite numbers can give us a finite sum. And that seems weird, right? But if you have, I'm going to actually show you a concept of this, but let's say you have a wall and it's 64 feet away. Then you cover half the distance. You've gone 32 feet. And then you cover half of that. And you go half and half and half. And if you were able to continue to cut the distances in half, they get smaller and smaller and smaller and smaller and smaller. And even though you physically couldn't measure them anymore, if I have 64 and I divide it by 2, I get 32. And if I divide that by 2, I get 16. Divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. And I keep going. Oops, 64. And I could keep dividing by 2 forever. And if I add all those back up, all those distances I created, what do they add up to? 64. Because that was the distance I started out with. Now I broke it into an infinite number of tiny little pieces, but when I put those back all together, I still get 64 feet. So even though I have all these infinite numbers that I could never actually write them all down, it still gives me a finite sum. And that's one of the harder things to wrap your brain around.
I can understand it.
Good. But it's like it's hard for some because you're thinking you can't even measure that. It's too little. You keep breaking it in half, and it's not physically possible. But
just do what you just did.
yeah, you just keep dividing by 2, and that'll keep going.
Multiply by 2, multiply by 2, multiply by 2.
Yeah. And when you add all those back up, you get back to 64. So even though you have an infinite string of numbers that you can never even see all of them, they'll add up to 64. Does that make sense? If not, let me know. Oops, that's not what I meant to do.